This podcast is brought to you by the Albany Public Library main branch and the generosity of listeners like you. What is a podcast? God, Daddy, these people talk as much as you do. Razib Khan's Unsupervised Learning.
Thanks for listening to the ungated version of the Unsupervised Learning podcast. If you want to read some essays on some of these topics, please check out razib.substack.com. Again, that's razib.substack.com. Thank you.
You know that genetics plays a huge role in our health, and more people are using genetic testing to determine risk for diseases like cancer for themselves and their kids than ever before. So I want to tell you about Orchid. It's the only company that does whole genome testing for embryos, testing before your child is born. If you're doing IVF, this is a clear choice now because now you can reduce risk for thousands of single gene disorders, including heritable forms of autism, pediatric cancers, and birth defects. Check them out at orchidhealth.com.
Hey, everybody. It's Razib with the Unsupervised Learning podcast, and I'm here today with Cody Moser, who is a second-time guest. Cody is a evolutionary biologist, behavioral ecologist, cultural evolutionist, evolutionary anthropologist. I don't know how many different types of things. He was actually, I think he was a physical biological anthropologist when I first met him many, many years ago when he was at A&M. So he's worn a lot of hats. He is a hat wearer as well. So that's apropos. And he has a paper out. And so I'm talking to Cody partly about Cody is he's a PhD student in Paul Smaldino's lab at UC Merced, and Paul I actually know from back in the Davis days, kind of casually, some of the Miguel Rith Lab's meetings on cultural evolution, and Paul's got a new book out on agent-based modeling. Actually reading the book right now. I haven't finished it. After I finish it, I will probably, just for you listeners out there, try to do an interview with Paul. If you guys want to get, listen to something nerdy about cultural evolution, we're going to dig deep. You know that I like to do that. Cody has a paper out with Paul in the Royal Society. Which Royal Society is this? Is this B?
Yeah, this is Proc B.
Okay, Royal Society B, so it's biology. And the paper title is Innovation Facilitating Networks Create Inequality. And that title seems, in a way, it's kind of straightforward and generic, but the paper itself is pretty interesting. There's stuff about agent-based modeling, experiments, network theory. So it's open access. You can read it, but not going to lie, it is pretty dense. And it's pretty complicated. I have more than a trivial familiarity with this field, but it was difficult for me to follow. So I guess the way I want to get into it is just say this is measuring potential ways that innovation occurs in groups, in different groups and in different group structures. And there's some non-intuitive stuff, and that's what you do science for. Well, except for psychology. No, I'm just joking. You do science to figure out non-intuitive results, figure out non-intuitive dynamics about the world out there that you just don't know ahead of time, right? And so this is showing that innovation isn't simply returns on population scale. So if you think about a big population should just have more innovations, have some linear scaling effect to it. But that's not exactly how it works. That's the result. You see it in the abstract. But they studied something called the potions task, and I told Cody before we got on that I've never done the potions task, so just reading about it is not really doing it for me. And so Cody, before we get into the results and why they're interesting, tell us what the potions task is. Describe it. Make it real to the listener.
Yeah, totally. And thanks for the introduction. So the paper itself is an agent-based model based off of an experiment called the potions task. And so this task was invented as an experiment to be done in person with people by Maxime Derricks and Robert Boyd, I think in 2016 or so. And basically what it was imagine a world where you have a set of 6 potions. Let's say you're making some kind of medicine or some kind of ingredient to do some kind of magic or something. And what you can do is you can take the different sets of potions and combine them to make new potions. And so in the experiment, what happens is people start off with 6 potions. They can combine them to get new potions. And when they get those new potions, they can then take those and combine them with the older ones to make more and more subsequent potions. What was significant about the experiment and the way that they comprised this task is that there was an initial bias towards a certain set of potions that you would make. So with that initial set of 6 ingredients, you could have combined them in 2 different ways to get 2 different subsequent potions. And so you would find something, you would keep on using that in subsequent combinations, but you would never go back to that original set and try and figure out what else was there. And so in this experiment by Maxime Derricks and Robert Boyd, what they did was they manipulated social groups of in-person people. So basically, they had 2 groups. One group was a group of 6 people all sitting together, mixing these potions, and they could see exactly what their partners had done. And then they had another group where it was 2 groups of 3, where in those 3 groups, they could see what their immediate partner had done, but then they could spy on the other groups every once in a while. And what they found is that it was only in that kind of broken up group that had 3 groups of 2, where people were able to basically find the top potion of each of the 2 trajectories. There were 2 initial trajectories of potions. Basically, you could imagine them as like 2 different tech ladders that you have to climb up if you've ever played the game Civilization, for example. 2 different tech ladders. And when you get to the top of these tech ladders, you could combine them. And they found that for these fully connected groups where everyone could see what everyone else was doing, basically none of those fully connected groups were able to find the ultimate potions. But over half of the partially connected groups, the ones where you had 3 groups of 2 people that could kind of spy on each other, were able to figure out the final potion, the task, and basically beat the game.
Kind of reminds me a little bit of the shifting balance and civil rights ideas. And so, because I tend to think of biological evolution whenever I see this cultural evolution stuff. And so I'm thinking, okay, so you have a massive population and a massive panmictic population that's like random mating. Selection is operating in these additive independent effects and it's reaching these optimum. And so Sewell Wright had this not totally coherent, well-realized idea, but that's very metaphorically attractive, that if you have broken up populations, smaller populations, drift and epistatic effects and other things will allow them to cross the barriers in the adaptive landscape and hit like these higher optimums. And what do you think about just that resonance for me? Like, is that off base?
That's not even off base. That's just totally true. So in our case, this goes back to basically a bunch of other findings found in the collective problem solving literature, where if you kind of break groups up, if you lower their rates of transmission, if you make agents less likely to change their opinion, what you do is you increase the so-called transient diversity of the population. That is, the population's ability to entertain multiple theories. So the philosopher of science, Kevin Zollman, in 2007 wrote a paper basically saying that this transient diversity thing allows people to find better outcomes in science. And so recently, Paul and I wrote a paper titled Maintaining Transient Diversity as a General Principle for Collective Problem Solving. And in it, we make this direct comparison to Wright's shifting balance theory. Because if you think about it, this kind of transient diversity argument is a structural version of R.A. Fisher's fundamental theorem, right? That basically the amount of variance that you have in the population is proportional to the strength of selection. And so in all these different collective problem-solving models, from this weird potions test we have...
the reverse, right? The strength of selection is proportional to the variance?
No, that's correct, yeah.
Yeah.
Oh,
you
just
said
the other way. Oh,
yeah. Anyway, I just want to get the causality right there.
No, you're right. Yeah, so
it's kind of true. Well, I mean, you're not totally wrong, because if you have really strong selection, the variance is exhausted, right? But anyway, I know someone in the comments might be like, well, actually,
no, that's totally right. Yeah. Sorry, I was kind of going flow of thought. Yeah, but basically, the idea here is that you want more variance in order to get more selection. And this is the case in these collective problem-solving models, that the more variance of opinions that you have, the better that populations tend to do. Now, the problem is that in this paper, the way we wrote it, it's like, oh, just add more variance. That's always going to be the way that you improve things. But if you sit around and you look in the real world, it's clear that we tend to talk to each other. We're not totally siloed out. I mean, in academia, we kind of are, but not totally. And so the question is like, why is it that these kinds of structures that seem to facilitate innovation in these agent-based models and mathematical models are not always present in the real world? And one of the thoughts that I had, I said, well, the thing is that we're looking at the payoffs for the group, but we're not really paying attention to the payoffs for the individuals in the group. So what we did was we followed a series of other modelers, starting with Andrea Miliano, who took this potions task, turned it into an agent-based model and basically ran it on hunter-gatherer networks, which was pretty neat. And we ran it on a bunch of different simulated networks that we came up with. And also some real-world networks, including the hunter-gatherer networks. And I made a collaboration network of my department at UC Merced. Turns out we actually kick ass at this thing. And what I looked into was in addition to group performance, how performance weighed out on the individuals.
Okay. So we've been talking about individuals and models and whatnot. I have been meaning to ask you at some point. Let's just do it now, early on. Agent-based models. I know Paul's got a whole, I've done some agent-based. I mean, back when I was, doing population biology at Davis, UC Davis, PopIO. This is like 10 years ago, so maybe it's changed now. I mean, there was a whole section on agent-based modeling. We would code it up in R and stuff like that. The guy who taught us was a graduate student. He left academia. He's working in quantitative finance. But anyway, give us the TLDR on agent-based modeling. What is this? Why is this so cool? I'm assuming it's gotten much further in the last decade than it was. It felt like a little bit very early and embryonic when I was working on it, when I was doing the problem sets in 2012.
Yeah. So it seems like the field's gone through like some dips and leaps, and right now it's definitely a huge leap. A lot of people are really paying attention to agent-based modeling, but pretty much what an agent-based model is it's a computer simulation that you could think of it like, SimCity or something like that, right? You're basically specifying the agents and the kinds of behaviors that they can have with each other when they interact. So what you do is you build in a number of minimal assumptions, just like a mathematical model, and basically just simulate it out. So in situations where, for example, you can't get an analytic answer like you might in many mathematical models, you might want to use an agent-based model to just simulate it out and try to find the limits across a wide range of parameters. And so like in our case, what we did was we said, okay, agents basically interact with another agent who they're connected with in a network. They combine one of the potions that they have at random with some kind of preference for a novel potion rather than an older potion. If they make a right combination, they get a new potion and they can give it to their neighbors, et cetera, et cetera. And from there, you can, alter some of the parameters like the network structure, the propensity of the agents to share with one another, and all those different things to see how those influence the outcomes on the population level.
All right. So my daughter is learning Python right now.
Whoa.
And the teacher, Cody, she's 11. Okay, guys, she's 11. But the teacher uses the word parameter all the time. And I realized, look, I know that a lot of the listeners out there, you guys are nerds, you know what a parameter is. But I mean, you just threw down a lot of technical terminology, Cody. Could you tell them what a parameter is and why that matters for agent-based modeling?
Yeah, sure. A parameter is some value which you can tweak in the model. So, for example, one of the things we have is the propensity to share. So an agent, if it finds a new potion, it can share it with other agents. If that parameter is set to 1, then that means that it's always going to give this new potion to its neighbors. If it's set to 0.5, it'll give it to about half of their neighbors. If it's set to 0, they just never share. So the parameters are things in the model that you can tweak to kind of find these critical behaviors in terms of your outcomes.
And your description of agent-based modeling, it's great. It's what I thought. I'm assuming that a lot of the reasons that people weren't using and still don't use agent-based modeling, because it's basically a simulation method, right?
Yeah.
And it's like simulating reality. It's simulating individuals or agents, operators, in aggregate that are interacting.
Yep.
I'm assuming that it's computation that's limiting the use. Otherwise, they would just be everywhere.
No, exactly. And so actually you find a lot of times in agent-based modeling literature, there's kind of, 2 different approaches to it. You have the simple minimal models approach, and I think that arises from a kind of philosophy of science perspective that says, what is it that we can get out of minimal assumptions? And those tend to be not so computationally complex, like this potions model. If anyone ever wants to run this thing, I have all the code on GitHub. It's a lot of fun to watch as a simulation. Pretty simple as well to implement. You just do it in Python, where basically what you're doing is you make minimal assumptions and try to get the most complex behaviors possible. On the other hand, there's another one, another perspective where basically people try to build the most complex models to try and fit the data as much as possible. So I've seen like agent-based models where people are like, I simulated the economy of Germany for the last 10 years to figure out what COVID impacts would do. And something like that, I can't even imagine trying to run that thing. I mean, one run must take like a month versus the things for me, they take about 30 seconds.
Well, you said philosophy of science. I think one of the issues that you're alluding to here is, preference for parsimony, Occam's razor. I mean, the simplest models, the simplest explanations of nature are usually just preferred, although that is a heuristic. They're not necessarily, there's no law, from on high that says the simplest models are the true models. It's just, they tend to be, I think partly just because, for complicated models, there's just so many models that you're going to explore that if the complicated model is the correct model, to figure it out is going to be really hard. Yeah. So you might as well just start with the simple models and hope that the simple model is really the explanation, right?
No, that's precisely it. Yeah, if you start with the simple model, you kind of squint your eyes and on a fuzzy level, you're like, well, I guess things behave like that. But it leaves a lot more open in terms of, like you were saying, in the case where if you build a super complex model, you better be pretty sure that what you're saying is precisely what's going on in the real world.
All right, so can you tell them what a connected caveman network is?
Oh man, so this is my favorite network. So this was created by Duncan Watts, I think, in like the 1990s. And so a connected caveman network is where you have these mini networks that are fully connected. So let's say that would be like 6 individuals, and they're all talking to each other. What the connected caveman structure does is it severs one of those links. So 2 of the people are no longer talking to each other, and instead creates a link to another caveman network that's doing the same thing. And so what this allows you to do is it just maximizes basically the modularity of the network. So these groups are basically little individual compact subunits that are talking to each other really, really deeply and only just barely talking to the groups around them. We tested... Go ahead.
No, talk about what you tested. Go ahead.
Yeah. So we kind of tested this one in the model because we figured one of the things that helps people in this task is being able to subdivide the information in some way. So if you recall, I said at the potions task, there's basically 2 trajectories. We'll call one an A trajectory, which is, a tech tree set by your initial set of potions that you look at, and a B trajectory. And basically what you want to do is you want to get to the top potion in both trajectories and combine them. Now, the agents are pretty dumb. Everything they're doing is totally probabilistic. They're just basically saying, oh, this one looks good. Combine it with this one with some probability. They don't know, hey, I'm looking at this. You need to be looking at something different. And so what the structure does is it allows this group, this work to basically be divided into groups. It creates biases in different pockets. And so what this connected caveman does is it basically amplifies these biases within each of these little groups. We call them cliques. And allows the computation of the task to be subdivided into individual components.
Okay. And so, and like right now I'm like looking at your discussion because, in this paper, obviously it sums up and, it's a great paper, obviously, but I'm just telling you guys, there's a lot. I mean, I don't know, like there's a lot that went into it, right? Like I'm sure Cody, there's a lot of like, this is not simple, like, thinking about how culture works, like in your armchair or anything like that. Like, there's some computing and coding and these technical terms. So, you found that populations of all sizes and clique compositions perform similar per capita when the overall number of combinations are taken into account. Can you unpack that for us?
Yeah. So one of the things that you would assume, and this is something that we've known for a really, really long time since Joe Henrich first started working on the problem of innovation, is that larger populations tend to innovate better and faster than smaller populations. So he had this model that's now known as the Tasmanian model. It's super famous.
Yeah. I remember reading the Tasmanian model literally, I think in 2005. I remember reading that.
Yeah. So
way younger than you, bro. It's like back in the day.
Yeah. So that model was brilliant. And basically what Joe found is that larger populations tend to have more variance. So going back to this idea of transient diversity. And so therefore they're able to both maintain complex innovations for longer, but also continue to grow their complexity. Smaller populations are not as good. But something that we did was we looked, because a lot of times in these models, what they do is they run the model for basically all the agents, and they call that one time step. So basically a network that has 5 agents in one step will basically make 5 combinations. A network that has 50 agents in one step will make 50 combinations. Okay, when we correct for that, when we basically say, okay, what's just the raw overall number of combinations made? Basically, population size is precisely the same across network compositions. So that means that for a population of 100 individuals, it takes basically as much work as a population of 10 individuals to do the same kind of discovery in this task, which was pretty shocking to me because something that happens, especially in random networks. So random network is one that you manipulate and you give it some assigned connectivity. So a connectivity of 0.5 means that half of the connections in the network that could exist do exist. With a larger network at 0.5, that means that individuals tend to have more neighbors because there's more possible connections to be made. And at 10, they tend to have far less. Nevertheless, they seem to require the same amount of work when going through this task. This seems to have something to do with the fact that basically the larger networks are transmitting information faster and can make more possible numbers of connections in one time step than another. But it was a pretty shocking finding for me that pretty much all population sizes take about the same amount of time when you just do the raw number of combinations.
Yeah, bigger is not always better, I guess.
Yeah. I mean, so in a sense it is, but if you just control for time and kind of one way, it pretty much all equals out.
Mm-hmm. Wait, what about so random link alteration as a form of in-group competition? Like, talk about what relevance is that?
Yeah, so going back to the original lab study, where basically what they did was they had it so that people that you split the group into like 6 groups or into 3 groups, 6 individuals, so it's groups of 2, and every once in a while they could spy on the other groups and see what they're doing. So in a lot of the modeling literature, this is like random link alteration. What you're doing is you're introducing new information basically by altering the structure of the network. You could think of this also like in terms of migration. A lot of studies kind of use that term to say, well, what if you just take individuals from one group and you move them into another group? So what we did was we just had it so that individuals after a certain amount of time steps had the chance to randomly find a different connection. It was not targeted, so they didn't look for, like, let's say, the best performing person, but they looked for a random person. And what we found was that there's basically no difference, which is kind of in line with what happens in a lot of the literature, which is that either people seem to find it makes a difference, some people don't. There's a good study on the show Doctor Who, where they found that the showrunners would randomly move the writing staff around to different parts of the season. And they found that when they did the most movement like that, they tended to have the highest TV ratings. But
wait, because this makes them more creative, or?
Yeah, basically. And also the people who run the Broadway show Cats know this as well, that basically they notice that if the actors are getting a little too comfortable with each other, they'll start moving them around to different show times. Basically, they think that keeping them on edge seems to increase their productivity. But here we found it didn't really make much of a difference.
I mean, there's something with that, back when I was like a spectator sports fan, especially NBA, NFL, whatever, baseball, they do these trades. And why do they do the trades? By definition, a lot of the times the trades are equivalent players. So like, what's going on here? And they're just like, well, there could be a new combination, and all of a sudden there could be new synergies and stuff like. You just never know, right?
Yeah. And basically, like, if you think about it, going back to kind of, as you were saying, with Wright's landscape, it's like if you took an individual who's on one peak, one adaptive peak, and you tried to move them to another one. There's several reasons why maybe we didn't find it in our model, specifically the fact that the link alteration is just completely random. But I think there are some manipulations you can make to basically make it work a little bit better. But we didn't do those specific manipulations.
So your agents, they're all the same, right?
Yeah, they have no differences in terms of their propensity to innovate or to diffuse information or anything like that. It's as if you just had a bunch of clones, and all that matters is where they're sitting in the network at any given time.
So this is like Homo economicus type stuff, right? Like they're all interchangeable. It's just contingency of where they're positioned and in the sequence of interactions. But there is, I think, like some of them are more productive. There's genius effects. So talk about that.
Yeah, so the major finding in the paper is that as innovation increases in these networks, so does the inequality. Okay, inequality of what, you might be asking? So it's the inequality of solutions that the agents have found. And so basically all of these measures, such as decreasing the population connectivity, making agents less likely to share, or basically increasing population size, also increases the inequality in the networks, meaning that some individuals basically have way better solutions than others. And so, I'm looking at this and I'm thinking, there's basically Isaac Newtons sitting in this network because as you tend to increase the productivity, you just have these super performers. And those are kind of the people that we're finding are kind of driving the inequality. What we find is that where they sit in the network, they tend to occupy positions that have what we call high betweenness centrality. Okay, what does that mean? In network science, it means that, let's say you're trying to get from you to the furthest person from you in the network. And everyone's trying to do that. They're trying to get to the furthest person from them. What individual does everyone have to pass through the most in order to get to that other person? That person would have the highest betweenness centrality. And so we found that these kind of really central people tend to be boosting the inequality in the network by basically being the highest performers as well. So you might think of them as basically bridging disparate parts of the information networks within these different network structures, and therefore driving the inequality up because they're able to kind of synthesize the information that the disparate parts of the network have.
I mean, it sounds like you're making the argument for multidisciplinary researchers, but...
No, exactly. And some economists of science talk about these as broker effects, that basically what you have is you have these people jumping in between different parts of the network and synthesizing information the way that it hasn't been done before. This recapitulates a lot of the work by James Evans at the University of Chicago, who's done a lot of work on scientific productivity, where he's found that basically these massive outsider effects in terms of scientific papers that tend to have high impact, where basically these highest impact papers tend to be people who are basically jumping in through what we would call topological holes in the network, bridges that need to be gapped. As these bridges tend to be fused, they tend to produce higher impact papers because they seem to see something that other people can't see. Go ahead.
No, go on. I mean, okay, you know what? So what I was gonna say is, Isaac Newton said, and there's a whole discourse or whole like literature about whether he's being sarcastic or not, but he stands on the shoulders of giants, etc. Right? And so that's like going in one direction. But I think, what I would say to what you're talking about here is sometimes outsiders, they see that what someone would see as like a wall, they see the door in that wall that other people don't. I'm using an evolutionary biology example. Some of I know Cody, Price equation, George Price. Yeah. He created an equation, a formalism that basically represented and reflected selection at different levels, at different orders of complexity in a very, very simple way. And W.D. Hamilton, the famous evolutionary biologist who really pioneered a lot of the work on, inclusive, he called it inclusive fitness. John Maynard Smith called it kin selection. But his paper from like 5 years before Price was really complicated. And Hamilton, in his memoir, Narrow Roads of Geneland, the first one actually. Like I own all of them. Like anyone who hasn't read them, they should read them. It's really good, especially Hamilton's reflections. But he was talking about how Price was an outsider. He was a physical chemist who got into a injury, a car crash with a truck. And so he was set for life because of his injuries. And he tried to figure out what he wanted to do with his life. And he decided to do evolutionary biology out of the blue. And so he created this like new formalism, just, not randomly, but, because he didn't start with any priors that conditioned him, And so this is why interdisciplinary work, this is why new people, fresh blood, new location. I mean, when people do sabbaticals, so sabbaticals, like, in academia, you take a year off, you learn new things. Most of the time, like, I don't actually know of anyone who's ever done a sabbatical. I'm sure that it exists where it's at the same institution. But most of the time, they go somewhere else. Why they go somewhere else? Well, because like new colleagues, new people to talk to, it might trigger them into new ideas, new paradigm, new worldview. What were you going to say before I interrupt you?
No, I was precisely going to build on what you're saying. So in another paper, I used this same task. This was done with my colleague, Jesse Miltzman, who's at the Army Research Labs, where we identified what we called loser nodes in these networks. So what is a loser node? A loser node is basically an individual who, when you're watching the performance of the network, it looks like they're not doing anything. They're hanging out on the fringes. They're just kind of on the sidelines of these networks. But when the network gets stuck, these individuals tend to be the most critical in terms of scaffolding innovation, precisely because they're on the edges. They're not subject to the same kind of information biases as the rest of the group. And, do you want me to kind of walk you through that paper as well, given that it's kind of the same thing?
Yeah, sure. Yeah, let's do it. Let's do it. Tell me.
Yeah. So this is a similar paper called Decentralized Core-Periphery Structure Accelerates Cultural Innovation in Agent-Based Models. So same task, it's the potions task, but instead of these connected caveman networks, we created what we call core-periphery networks. So a core network is one where basically everyone's highly connected to each other, right? Everyone's talking, everyone's doing the same thing. And the problem with that is that when everyone's highly connected to each other, they tend to amplify and share the same biases. So what you want to do, which is basically what we found in this network or this paper on inequality, is you want to break it up into groups to increase that transient diversity. But in trying to isolate this loser node phenomenon, we basically used a network formation algorithm called stochastic block modeling, where what you do is you define two different network groups, you define how connected they are to themselves, and then you define how connected they are to each other. And so we created what we call decentralized core-periphery networks, where you have one core group that's very connected to itself and a periphery group that's neither connected to itself nor really to this other group, basically amplifying the production of what we call these loser nodes, nodes that really aren't talking to anyone. And what we found is that even better than these connected caveman networks, these decentralized core-periphery nodes tend to innovate much faster and at higher quality than other network structures. Now, why is that? So going back to what you were saying before, there's this old idea of explore-exploit dynamics. So in this kind of explore-exploit paradigm, the idea here is that when you're doing some kind of information search, you can either look around for the next options, or you can use what options you have available. In a highly connected group, they're all basically using whatever information they've got. They're not really searching. They're not looking for anything new. But in a less connected group, what's happening is the agents are basically looking around a little bit more. They tend to explore more. And so in these decentralized core-periphery networks, you tend to have one half of the network that's highly exploratory. These are the loser nodes. And then one which basically takes that information that they get from the periphery and they use it immediately. And so, this goes back to some of the ideas that you see in organizational science with, say, like Lockheed Martin created Skunk Works, where they basically separated part of the company from the rest of the company to kind of scaffold innovation. Steve Jobs did this with the Mac division at Apple. And over again, you see this in a bunch of other places. So bringing it back to genetics, Ernst Mayr discussed this as one of the ideal populations for scaffolding selection because he was very worried about genetic swamping. This idea that even if you have a selective variant, it's hard for it to overcome pretty much all the bad variants in the population. And so he said the ideal kind of population that you have is one where you have one really big core group, and then you have a bunch of peripheral groups basically feeding in through migration the selective variants that they're discovering. Basically as a way of creating like a backstop valve so that the bad variants can't get into these peripheral populations.
Yeah, I mean, what Cody's alluding to also, like, and this is like outside the purview of this this conversation. There's a whole argument in evolutionary biology that goes back to the Wright-Fisher controversies in the 1930s and 40s about large breeding populations versus structured breeding populations. R.A. Fisher, the arch selectionist par excellence, like, well, I mean, really, like, he wrote, Genetical Theory of Natural Selection, created modern evolutionary biology that, fused, mathematical formal thinking with evolutionary science. He believed that basically everything is some large random mating population, and then Sewell Wright and others, Dobzhansky, obviously Mayr, they thought structured populations were relevant. I think as we're going forward, I do think the specific models that Wright, I mean, he was the model builder of that group.
Yeah.
Or Mayr was like just some verbal models, but not really mathematical models. Those models don't turn out to be right, but I think most people now do agree that Fisher went too far in just assuming a large random mating population, and that sometimes adaptation and selection actually does work better when you have smaller fission with smaller structured populations, right? I mean, that's my understanding. Like, I don't read all the papers. I read the abstracts. I don't read all the papers in that literature. I mean, I used to be super interested in it, but finite amount of time. Listener. I mean, I have other things to do, like this podcast. So I think there's a lot of analogies here. I'm thinking of like this network theory, hot and cold chains and MCMCs, where you have a parameter space and you're converging into a certain part of the parameter space, and then a hot chain has like a flatter distribution and can cross the parameter space and like kind of like look for other options. So it's all kind of the same in a way. These models are converging on the reality that a little bit of lumpiness in nature seems to be the best at generating complexity, and in this case, complexity and cooperation and innovation, right?
Yeah.
So I got to ask you, all your agents are equally dumb or smart. What's going to happen when you introduce a von Neumann agent in there? You know what I'm saying? I'm just curious. Like, I mean, are you guys like thinking about? I'm assuming the compute would be like more intense when you start to vary the agents themselves.
Yeah, so basically, I think what you're getting at is basically altering their skill distributions in this way. So there's a really great literature that I haven't gotten into enough, but is kind of a direction I would like to head in, which is, we have all these findings in game theory, and they're great, and, we're able to identify stable equilibria and basically idealized or ideal population structures for basically scaffolding cooperation in a bunch of different games. There's another one called the ecology of games, where it's like, well, let's just imagine that there are a bunch of games out there in the world, and that instead of playing just one game with someone, I have to play multiple games, or I have to play some game with someone that they prefer so that they'll play a game that I prefer. You scratch my back, I scratch yours, et cetera, et cetera. And so one way to think about this is, and I think we discussed this a little bit in our transient diversity paper, is that what is a common assumption in basically all these collective problem-solving models is that everyone is solving the same task, that they all have the same kind of problem. It's all the same, difficulty in some way. But really, once you start saying, okay, well, actually, there's different tasks people have to solve. They have different propensities with which to solve them. I think that would actually start to kind of break this literature up a little bit. Kind of setting it along like a future kind of complexity scaffold in terms of things that we can look for. And that's kind of a direction I'd like to take in the future, but maybe not right now.
Well, so I think in lieu of these agent-based models and the simulation stuff, it's kind of in lieu of doing behavioral economics and experimentation, right?
Yep.
And talk about the pros and cons of that, and also could you just allude to? I mean, we're talking about your paper and your research, but behavioral economics had a massive boom after 2008 in the financial crisis, before your time, but Dan Ariely, predictably irrational, all this stuff, and now there's some issues. And so, maybe allude a little bit to that in terms of like how people are feeling, and maybe that's explaining agent-based models in a way, because your code's there, bro.
Yeah. So behavioral economics, it's an awesome field that's basically, let's assume that people are rational actors, or even let's not assume they're rational actors. Let's kind of see what decisions people make under specific constraints. So if you interview Paul, you'll kind of find that he talks all the time about experiments are models too. They're just models that you kind of run, holding some assumptions with people, for example. So in behavioral economics, what you'll do is you'll come up with some kind of game that people play. But the trade-off is that it's really hard to do these at scale. So if you look at kind of the first agent-based model of this potions task, I wasn't the first one to do this. It was Andrea Miliano and a bunch of colleagues, where what they wanted to do is they wanted to look into hunter-gatherer networks. Now, could you imagine just like going up to a bunch of hunter-gatherers and be like, hey, start combining these potions?
Hey, you know what? Okay. pretend that I am a Kalahari-san Bushman. You know what I would say to that? No.
Yeah, exactly. Like people aren't just gonna like spend time. So if you kind of make some, weak assumptions, and you say, okay, what really matters is, something like the network structure. And we could talk about what a network is and whether or not a social network is actually a thing out in the real world. If you just kind of make those assumptions, then what you can do is you can kind of introduce a model to say, well, it kind of probably works like this if you squint your eyes in a certain way. You're getting general trends, but you don't get, I think, as in-depth, coverage of what's happening in the real world as you might with behavioral economics.
Okay. Yeah. I mean, and also with behavioral economics, like, most listeners know about the weird effect. They're college students. You might not be able to get a Kalahari Bushman or an Aceh from the Amazon, but you definitely could get UC Merced undergrads. And I mean, I don't know, Cody, if you want to generalize about human behavior and human nature from UC Merced undergrads.
No, I don't think so. Not at all.
Well, I mean, so this paper is very, very abstract in a way. It's a modeling paper, and you're talking about networks and caveman networks and all this stuff. Like brass tacks, like let's bring it back to reality. We've already alluded to some of the issues or some of the relevances. It seems to me that okay, one thing that I took from the paper is breaking people apart into groups is better, because otherwise conformity biases can sweep through groups. Is that correct?
Yeah, precisely. Yeah, people will create their biases that'll create a pocket of information that people really aren't good at traveling outside of, and basically put them on a specific trajectory. I mean, this is why it's also important to kind of make room for outsiders in science, I think. I think specifically, like in my own philosophy of science, I think about someone like Freeman Dyson. This is a guy who never had a PhD. He made significant contributions to physics, but for all sakes and purposes, in some aspects, he was a bit of a crank. Like he would like say things like, I have a mathematical model of, the immortality of humans if we can get our energetic constraints under some threshold or something. And people would be like, all right, sure. But while he's producing all this crazy stuff, he made a lot of important contributions, specifically, I think, because he wasn't trying to look where everyone else was looking.
Yeah. I mean, one of the things that, does worry about me about modern science with social media in particular is the collective communal community aspect of it.
Yeah.
And kind of like the decline of ornery jackasses.
Yeah.
Not that everyone, I mean, look, I've had to deal with the ornery jackasses like back in my day. But ornery jackasses keep you honest.
Yeah.
And I do think it's a problem. And when you're talking about the bubble and the pocket, I mean, that pocket and bubble could encompass a whole nation.
Yep.
So we have this information technology that's like tying us all together. And in the 1990s, we had a dream when we would all kind of like figure things out and like discover everything and all this stuff, and it would be great. And what we see is there's these information bubbles now.
Yeah.
I mean, like, let's say the public health community during COVID, they flipped or anti-mask, pro-mask, all these things. I think, I think I can say this pretty uncontroversially. This wasn't science-based viewpoint. It was group conformity. This is what the other people in their community said. And I've said this before, like, there are scientists who are like, they're in the science for the community. And I'm like, this is a problem.
Yeah, totally. So I've been writing a little bit in addition to my scientific work. I've written some stuff on Substack and for Quillette and for this magazine, The Hungarian Conservative, specifically talking about some of these effects in terms of our internet architectures. So, like, if you think about what's happening with the internet now, there's like 3 websites. I used to have so many forum subscriptions. I'd have to log into individual things to talk about like my niche interests. I mean, that's gone now. Essentially what's happened is we went from a pretty balkanized internet to one that's so centralized that information is just like coming at us like a fire hose. And pretty much your only chance to kind of survive in that environment is to very quickly coarse grain the information, who you're getting it from, who you trust, and then immediately you get something like polarization. It would have been awesome if the internet kind of stayed in this, less efficient structure. I think it's horrible that, for example, I don't want to make fun of Reddit too much, but sorry, Redditors. But basically, the death of the comic book guy, this kind of snob who kept everyone on their toes. I think that actually this comic book guy kept a lot of, niche things kind of in high quality versus,
You're talking about some person on Reddit?
Well, I'm talking about, basically a lot of things that used to be niche interests.
I got it. So the guy who worked at the comic book store, this like 55-year-old guy, who had never known woman, but he knew everything about comic books. Oh, and there's the same guy at the video store.
Yeah,
he was a video guy.
Yeah, and basically these kind of niche specialists, I'll call them specialists, in whatever their hobby domain was, kept these hobbies and maybe much of the culture at much higher quality. But now, basically, everyone's having to enjoy the same things. They're playing, back to, well, there's regression of the mean basically happening culturally for so many reasons, especially on the internet.
Interesting. So, I mean, aside from science, I was just thinking innovation more generally. There are cultures that are known as more conformist and cultures that are known as more individualistic.
Yeah.
Cultures that have more diversity culturally and cultures that are more just like huge mega cultures. So, for example, we got to say it, like the People's Republic of China is this massive mega culture where now the latest, I was just checking it out, 80% of people can speak standard Mandarin, Pengtua, I think is whatever it's called, and 95%, more than 95% can read it, obviously because it's a unified written language. 80% of 1.4 billion is a lot of people, obviously more than a billion people, so like 1.5 billion or whatever. And so, or not billion, 1.2 billion, but so you have all these people with all these ideas, and they do produce some great things called create, like Three Body Problem, out of the People's Republic of China. But one of the things that I wonder about, because they do have an issue with the lack of civil society, partly because the party, the CCP, crushes civil society, that these like massive mobs and conformity biases can come down in WeChat and other places. It's even hard for the party to handle them sometimes. And I just I'm thinking of that as I'm thinking of like your model here.
Yeah. I mean, you have to think like they have designed, and Paul had a grant where I was a researcher on it to kind of look at this idea of information architectures as they kind of vary between the West and the East. And we're doing some work on basically propaganda flows in different networks. But basically, if you think about the way that like the Chinese information architecture was designed, it was pretty much there to hold central control. I mean, it was designed to be centralized. But the problem is like you said, once some kind of snowball effect starts going, that massive centralization is just going to make sure that it, goes indefinitely. But if you break things up, there's at least, like we were talking about earlier with the core-periphery network, some kind of backstops to the information flows in the networks. And I think we need more of that. Paul has a paper, it's really awesome, where basically it's a paper where they use these connected caveman networks to induce polarization in a population. And what's really cool is that when they increase the number of topics over which individuals can disagree over, basically they create a hyper polarization where everyone is disagreeing over so many things that eventually it kind of it basically levels out, where the overall polarization of the population ends up decreasing. And so you can kind of think of that like basically if you subdivide the population as much as possible, eventually you won't have these kind of great centralization effects.
I mean, it's interesting because we were talking about like the Tasmanian model, and as you indicated, the Tasmanian model is this isolated population, and it starts losing innovation. It starts losing technology.
Yeah.
There's just meme loss. Let's just put it that way, right? Cultural simplicity. And then you have this. So, okay, let's do the inverse of the Tasmanian model. Let's have every person in the world can communicate with every other person in the world. What you're trying to say here, it sounds like, is that is not this sort of like flat, homogeneous bubble of humanity is not the path to which makes sense, because it's kind of like a little bit like, in terms of a network, it's kind of like a slime mold or something.
Yeah Well, I mean the big book that influenced me was and you're going to know this, is Walter Scheidel's Escape from Rome, right?
Oh yeah
Like, where basically he says, what really helped Europe basically achieve what would, become industrialization, or at least become the Enlightenment minimally, was the fact that Rome collapsed. Thank God Rome went away, and, Europe ended up fragmenting. They shared a common language, so they still had a communication channel through the Catholic Church. But basically by subdividing the European continent into different parts, you basically had these micro experiments happening all over the continent. And that was something that really bolstered our innovation during that period of time.
I mean, Jared Diamond, Landy, there's a bunch of people that have this idea that Europe's Balkanization was good, actually. And it's interesting, if you read, this is, again, a situation where being inefficient is good, because if you read Brian Ward Perkins' stuff, like listen to Patrick Wyman's podcast. Yeah, I mean, actually, anyone should listen to Patrick Wyman's podcast, Tides of History. But they will talk about economies of scale and efficiencies. Industrial efficiencies started emerging during the mid to late Roman period, during the imperial period, that were never achieved until the 18th century again. Mm-hmm. Massive efficiencies were lost. There were consumer goods, plates, pots, other things that the Roman Empire was transporting mostly through water, but whatever. These sorts of efficiencies did not emerge for 1,000 years. But what did happen over those thousands of years is different European polities undertook experiments and were competing with each other. And that produced a totally different dynamic than if it was like competition within the Roman Empire of like firms and individuals, I guess, because you would think these firms would compete and they would discover the moldboard plow and the water, the windmill and all these other things, but maybe not. Maybe they would be stuck on a local optimum and try to squeeze more efficiency out of their slaves. So some of this is the difference between like endogenous growth theory and innovations versus Smithian growth. Smithian growth, Adam Smith's growth, is like cooperation, efficiencies, comparative advantage, and so you can grow on the margins. You squeeze more out of the same. That's what Rome was doing. And what the collapse of Rome did was a massive regression in lifestyle and in economic well-being, like the collapse of the taxation state to an in-kind state of service, the feudalism. But it eventually ended up to be, where like here we are with a modern technological civilization. There was this path through this lumpy political system. Whereas China, and if you guys read The Great Divergence and other works, like they've got really good at efficiencies. Like they brought New World maize that led to the spread of the Hakka into South China, and extra cultivation. China's population doubles over 250 years, which is like a lot in a pre-modern world. But they were up against the limits of efficiency. They never really figured out innovation, and we wouldn't exist if it wasn't for Haber-Bosch process. And if you guys don't know what it is, I'm not gonna tell you what Haber-Bosch process is. If you're an adult listening to this podcast and you don't know what Haber-Bosch process is, Google it. But that is why we exist. Without fertilizer, we would not exist. We create miracles from the air, basically. Which your paper is abstract, and I don't want people to get a little intimidated and overwhelmed by what is an agent-based model and network topologies and all these things. This is all like the stuff of the world that we live in, right?
Yeah. And one thing I'll say real quick, because you're talking about these kind of Smithian trade-offs and whatnot, is one thing I don't want people to walk away thinking is reading my paper and say, oh, well, the total thing, the medicine, the antidote to all issues is to break the population up. It's really task dependent. So if any of your listeners are familiar with this idea of no free lunches theorem, it's that basically any kind of search process across the diversity of potential tasks out in the universe does as well as any other search process. So the structure of these networks and their performance is dependent on the task that they have to do. So Lazar and Friedman in 2007 did a similar task to what we did here. And they found that actually when the problem is simple, when pretty much what you need to do is get everyone on the same page, the simple networks do fine. But when you have a very complex task, something like the connected caveman or something like, full-scale innovation, breaking up works in those instances.
I mean, it sounds like this is, news you can use. A lot of this work is, I know you work, some of your work is industrial science in terms of social psychology, basically how corporations can be more efficient, right?
Yeah. Totally links into the organizational science literature. Yeah.
I mean, this could be like a chapter in a Jonah Lehrer book, some of the older, you remember Jonah Lehrer, right?
Yeah.
Yeah. I mean, this would be a chapter in the Jonah Lehrer book. Future Jonah Lehrers, I know there's other Jonah Lehrers out there. I think that this would be a great chapter in a book where it's the chapter title could be do more, be less efficient.
Yeah, precisely.
Yeah. So where are you going with this work in the future? Tell me, give me a general sense.
Yeah. Right now there's a few different things I'm doing. We're looking at, we did this thing where I created a collaboration network of my department, and found that we're pretty good because we tend to have a lot of peripheral nodes, people off working on their own problem, but then, that information comes back to the rest of the group. Now we're looking at, say, for example, networks of philosophy throughout history. So what does the information transmission in the Vienna Circle look like? And was that something positive to building its discourse?
Wait. Tell people what the Vienna Circle is.
Yeah, so the Vienna Circle is this mid-20th century group of philosophers who rose basically centered around Vienna. They made a lot of contributions to, positivism and the reaction against it, like Karl Popper with
logical positivism.
Yes, that's right. Sorry. But that's kind of a critical era for 20th century philosophy. And what you can do is you can kind of look at the interactions between individuals in those networks, either how they were attacking each other, how they were agreeing with each other, and try to get some level of productivity out of those. And so we're looking at some networks. That's with Tyler Margettis at UC Merced. With Paul, I'm exploring some of these. Well, what if people aren't just kind of maximizing the same thing? What if you're maximizing a bunch of different things? But I mean, there's so much work to be done in this space. Innovation studies and collective problem solving, more generally, collective intelligence, is a really hot topic right now. I had a paper recently titled All Intelligence is Collective Intelligence, where we started looking at basically principles that align the groups of neurons to the groups of, say, individual people out in the world to biological populations, trying to figure out what's going on there, doing some history of science to figure out, actually, are these different models or is everyone pretty much just copying right? There's a little bit of evidence to show that, which is really interesting. But yeah, so a lot more to come kind of in those veins.
All right. So a couple of things. First, I want to say Vienna Circle, logical positivism. There's a lot of people associated with it. You mentioned Karl Popper. He wasn't associated with it. He was kind of on the outside of the circle, and he popularized something called the Popper legend. He killed the Vienna Circle with falsification, but they don't actually think that he killed it. So Popper was, the whole idea is like, open society and his enemies. That was like Popper's idea, but people say Popper himself was really self-centered and like would not accept any disagreement. Like he would just not let anything go. So people would just not talk about anything that they disagreed with him about because he just would not let it go. Okay. I want to, but Rudolf Carnap, who's a little older than Popper, was a central figure in the circle. And he had this thing where, Popper would talk about the differences between his falsification and Carnap's ideas and the Vienna Circle's ideas of, positivism and, confirmation. Right. And Carnap said, I think I've told this story before. I just think it's funny. Carnap said, the distance between Popper and me is very great. From Popper to me is very great, but the distance from me to Popper is very small. Which basically meant they didn't think that it was like that big of a deal and that he was that different. But from Popper's perspective, it was a huge difference, which is ironic in light of his role in philosophy of science and objectivity and whatnot. Also, I have to say, I had Michael Mutakrishna on. Oh, yeah. About a month ago now. People who are listening, well, actually, it'll be a couple of months ago when I post this probably. And he has a book, Theory of Everyone, and he's obviously a cultural evolutionist, Joe Henrich student. So that whole, and you mentioned Boyd, and Henrich is Boyd's student and Boyd is Richardson's student, whatever. That's the genealogy. But Joe has talked about collective intelligence and this sort of thing. One thing that I would love at some point in the future is like psychometricians get together with cultural evolutionists, because I think, look, Von Neumann's Von Neumann. Like, I don't care about what you're saying about collective intelligence. If you get like a bunch of me's together, we ain't gonna Von Neumann,
Precisely. Yeah. So in our paper, we kind of make this distinction between what we call agent positive theories of innovation. So this is one where what matters is having important people basically do innovative tasks. So this is like where you want a Von Neumann. Versus agent negative perspectives, which says, well, it's not the people, it's the structure. Obviously, rather obviously, it's a mix. Like the idea that, there has to be, if you think about it like a, like some kind of catalyst or something, there has to be basically a receiving end for these geniuses to be able to do the work that they're doing. And so I feel like that's like a lot of what the contribution I'm doing here is okay, well, let's assume that this person's able to get in their spot. Where's the kind of place that we could put them to make these things work?
Yeah, in a way, I think it resembles, discussions in economics with institutionalists versus those who want to emphasize human capital more. Institutionalists basically just put the institution there and they will come and they will produce and all this stuff. Whereas like, if you're talking about human capital, and I just did a podcast with Philippe Lemoyne, philosopher of science, and he just basically says, and I've looked at some of the quantitative data more recently, actually, it's shocking. Immigrant stream in the United States is much more educated and high skilled for almost every single part of the world. The only exception is Mexico, where in Europe, when you compare to Europe, in Europe, Mexicans, and there are very few Mexicans in Europe, they tend to be more educated. The Mexican middle class will go to Europe, whereas in the United States, the Mexican working class, lower class tends to come to this country. But in every other case, in every other region of the world, we get much more educated, much more skilled immigrants. And Philippe Lemoyne's point is people are always saying, oh, America has like this philosophy and this culture and this politics that assimilates immigrants. And, he says it in a French way. He's like, no, it's the raw material matters, so that the Philippe talks like that, right? Like the listeners who listen to that podcast will recognize it. And it's basically like, it's not the institution here. Although he does say it's somewhat the institution maybe, but look, like we have all these comparisons, and in Europe and all these different groups in all these different countries, and they all like, lag in terms of education, employment, and they commit like higher crime rates. And he's like, but the commonality that they have, because like, in UK, it could be Pakistanis, and Netherlands, it could be Moroccans, whatever. Commonality that they have is they're way, way less educated and way less skilled than their equivalents in the United States.
Right. And I do think that's an effect. But then the question would be like, why is it that the more educated ones are choosing the United States, right? Like
opportunities.
Yeah. Precisely.
There's a positive correlation. There's a confound is what you're saying.
Yeah, it's not just, all the smart people just randomly pick the United States.
Like, here's the thing. If you're an immigrant, like brass tacks, like, for example, if you're a doctor who's trained abroad and does his residency abroad, you have to redo a residency here.
Yeah.
There's a lot of barriers that certain professions make in the United States, but it's not like that for business. It's not like that for entrepreneurialism. My understanding is in Europe, large parts of Europe outside of maybe the Nordic countries in particular, and maybe London, England area, it's just really hard to do startups for various reasons. And so if you're an immigrant, like you could do a mom and pop shop, but you're never going to be like, startup superstar unicorns in Europe. And aside from like Spotify and Skype, there's very few that come out of Europe, whereas the United States, and they're all not, it's not like they're from North Dakota,
Yeah.
They're not even from Ohio. I mean, I'm giving a populous state, right? They're from the Bay Area and to a lesser extent, New York, Texas, Seattle, and LA. But it's very, very few nodes of productivity and creativity that have the institutions, the synergy that brings it all together to leverage the human capital. And people see that. So, of course, like, if you want to be big and you want to be the best, if you want to create a unicorn and you are one of the best engineers in India, are you going to go to England or are you going to go to America?
Yeah.
You know where you're going to go. You know?
I loved a good book that gets into this a lot. I know you've had him on the podcast, is Matt Ridley's How Innovation Works.
I should reach out to Matt again. Yeah, he's a great guy. Yeah.
Yes. In that book, he's like, look at the Fortune 500 companies. He's like, if any of them are European, they were founded like 70 years ago. They're just these legacy companies that really don't have much innovation going on. They just have these power dynamics of rich get richer. Versus you look in the United States and it's like, our Fortune 500s are like dying and then resurrecting, over and over again. There's this kind of what Joseph Schumpeter, the great economist from Austria, would say, creative destruction. Our ability to basically cut down variance to get higher performing ones is really high in the United States. We have this ability to basically fail in a way that things can't over there, and therefore you just have increased innovation here.
And thank you for coming on. Is we're talking about diversity and structure and all this. Back before the recent troubles with China, I was thinking that, America could be the font of innovation and China could be the world's workshop. So you have the engineers in China and the scientists in America, and you could have synergy and synthesis. And we still kind of have that, I mean, we haven't totally decoupled, So not everyone needs to have, there doesn't need to be a Shenzhen Valley.
Yeah.
Okay. Gordon R. Dixon, a late Canadian, actually he's from Minnesota, he's Canadian, science fiction author. He had something called the Kildee cycle science fiction world where there's different worlds with different competencies. And there's one world where there's scientists, and then there's another world where there's engineers. And obviously it just shows you that the two groups, and so there's another world that are farmers, whatever. The point is that you can have structure, you can have difference, you can have variation, and you have complementation and synthesis, right?
Yeah.
And if we could view the world like that, I think it would be a lot more chill. Because I don't see, China's got a lot of great scientists, and they make up for it in volume in a way because they have so many people. Like, I can tell you, I have friends in plant genomics. They're like, these people are not making stuff up. These are legit results and legit science. And we're not going to be able to get the postdocs here in the United States. They're staying in China now. And they're good. So they're not all whatever. On the other hand, don't bet against America.
What is it that you always tweet? If you come at the king,
you best not miss. Yeah. So anyway, with that, I think this was a fun podcast because now we're quoting The Wire. Start out with network topology and agent-based modeling. I think people have seen the full gamut of my interests, like what I talk about. You know what I'm saying? Full nerd to whatever, But so it was great talking to you. Hopefully, well, actually not hopefully, I will be talking to your mentor at some point about the new book. Great book. Agent-based modeling. What was the? Is the title just agent-based modeling?
I have a copy right here. It's called Modeling Social Behavior.
Modeling social behavior, and that it's really good to go along with Richard McElrath's book about social evolution. There's some really great things in there, and I think it's good that people think about evolution. This is I'm going to channel David Sloan Wilson here. Think about evolution as a process that's more than just genes. Which that's what was my training and my orientation. Everyone knows that, but whatever. It is more than just that. It affects the world all around us in a lot of ways. And, obviously it's fascinating. I think it's fascinating. I think this paper's fascinating. The links are in the show notes. Like, check it out, read it,
Yeah.
listen to it. And thank you for being on again, Cody. It was great.
Yeah, always. Thanks again for having me.
Whole genome sequencing is used for adults and children every day to assess risk for thousands of diseases. Orchid, a genetics company led by scientists from Stanford, is able to do this for IVF embryos. Now, instead of waiting for a diagnosis, parents can assess if their embryos have genetic variants known to cause severe conditions before their child's even born. No other tests can detect these issues so thoroughly or so early. So check them out at orchidhealth.com.
This podcast for kids